Good day. Just like that, we are back again. So let's finish off this Newton's laws. So we cutted the previous video short because of the length. So let's just finish off where we left. So I was still explaining the types of forces and what you need to know to master Newton's laws. So now we are on tension. So let's talk about the tension force. What is the tension force now? So tension, this is a force that exists in strings or ropes, right? So this force exists when two objects are pulling each other with a string or with a rope, right? So this force depends on the object that is in question. But however, depending on the objects or on both objects, the tension will be the same. So the tension will be equal in both objects, just that they will be opposite in the direction. The direction is the one that will be different. So let's have an example so that I can show you how you can deal with this tension in different objects. So perhaps let's say we're having two objects. We're having object A there and we're having object B there. And these objects are pulling each other with a string. And let's say this is where the force is being applied. Right. So when you are doing the free body diagrams, you are going to understand this better. But let me just show this. So we need to understand where tension is going in these two different objects. So this is object A. In these two different objects. So according to A, since A is being pulled, so it means that this is tension, it will be acting in that direction. So this will be the tension of the body A. So it is acting as the applied force to the body A. But since this is being applied to body A, so it means that body B will also have the tension in the opposite direction now. So this is also more like the action reaction forces. So if the action is done, there will be a reaction. So it means that the tension according to this object B now, it will be in the opposite direction to that which was given by A. We can also have another example. Let's say now we are having other objects that are going in the opposite direction now. So we can have our body A there and you can have our body B there. So A and B. So let's say that now the force is applied to A and the objects are going that direction. So it means that now the tension according to block A now, the tension will be going backwards. So it means that tension according to A now, it will be backwards. Since this object is the one now that is acting like it is giving the applied force to block B. So it's giving the force to block B so that it can pull block B. So now it means that our B now, the tension will be in that direction. Just know that these tensions, they'll be in opposite directions. So on that object that is behind, the tension acts like the applied force. So one thing that I can explain as well when it comes to the tension or the objects that are pulling each other, always remember that these objects are moving together. So it means that accelerations of these objects will always be the same. They will have the same acceleration. They will have the same tension, just that they will be in opposite direction. So it means that tension according to our body A there, our tension now, it will be acting as our tension according to block A. Since our objects are going there, it means that our tension to body A is acting as a negative. So according to block A, we are going to have a negative tension. And block B, since block B is going the same direction where the tension is going, so it means that our tension according to block B, it will be a positive tension. something like that. So let's move on. Let's talk about the applied force. So now, what is the applied force? So this is the force that is given to the object to start the movement or to cause the object to accelerate, right? So in cars or in machineries, this force is given by the engine. So the engine gives the force applied like that. So that is the force applied. So I just saying there are two cases, but actually there are not cases here. We just talk about the force that is applied. So if the force is applied like that, not at an angle, it means that in our equations of motion, we are going to use this force since it is parallel to the plane. So we're just going to use this force. However, in some of the situations, we can have the force here that is acting at an angle now. So if the force is acting at an angle, we are going to have a different scenario. So this is force applied. So this force applied, we explained in vectors that this force applied has two components. It has the x component and the y component. So our x component will be something that will be here, our f at x, that will be parallel to the plane. And we have our f at y, that is perpendicular to the plane. So in our equations of motion, we are going to use f at x. And remember, we said to calculate f at x, we use what? F at x is equal to f cos of theta. And to find out f at y, we said f sine of theta. So don't forget that. That is very important. So now we can move on from the force applied. Let's talk about the net force or the force net. The force net. So what is the force net? So this is the sum of all forces acting on an object. The sum of all forces acting on an object parallel to the motion of an object. So these forces must be parallel to the motion of the object. So if the object is going to the right, it means that we must take all the forces going left and right and add them together to find our F net. So if we're having four forces acting parallel to the motion, then it means that our F net becomes F1 plus F2 plus F3 plus F4, like that. But however, don't forget that we are dealing with vectors. So what is important in vectors? It is direction. So also remember that in physics, there is nothing that is actually negative. The negative only shows us the direction in which something is moving, or the direction in which quantities are being shed. That is the direction. So in terms of Newton's laws, we usually take the direction of motion as the positive direction. So it means that if our object is going to the right, so it means that each and every force that is going to the right, it will be positive. And all the forces that will go to the left, they will automatically becomes negative. It doesn't mean that this force is negative. It just means that this negative is giving us the direction. So this is the importance of direction when it comes to physics. So now let's suppose that of those four forces that I talked about, maybe force 3 and force 4 are going in the opposite direction of motion. So it means that for us to find the F net, since F net, it is the sum of all the forces acting on an object, it will mean that our F net becomes F1 plus F2 plus minus F3. So this minus is indicating the direction. Since we didn't put any sign here, we know that we cannot put a positive on something that is already positive. We can let it like that. And also plus negative F4. So the negative is indicating the direction. Always remember that. That's why most of the times when we're dealing with Newton's laws, we find our frictional force mostly as negative, because frictional force acts opposite to motion of the object, and our force applied are mostly positive, because this is acting or going in the direction of the motion of the object, right? So this is the F net. So once you know how to make the that F net, or how to find the F net, you are halfway done to knowing Newton's laws. Just know how to calculate the F net, checking all the forces acting parallel to the plane. So once you are able to do that, the only thing that is left is for you to understand how to draw the free body diagrams. So we are going to explore on how to draw the free body diagrams and all the tricks that you need to know for you to be able to draw the force diagrams, the free body diagrams, I mean. So there are two ways of representing the forces acting on an object. The first way being the force diagrams. So the force diagrams are represented by straight lines. So the forces are represented by straight lines. So these straight lines, they have an arrowhead. So the arrowhead will be showing the direction where the force is going. So this is showing the direction of the force, and the tail will be coming from the object, while the object is being represented by a rectangular shape or a box. So if we can draw the force diagram of an object, maybe it is having 4 forces acting on it. So it means that this object, we have maybe F1 is going to the right. So this is how we show our F1. And then maybe we are having F2 going to the left. So we can have our F2 going to the left. And maybe we are also having F3 going up, maybe. So we can have a situation like this. So this is the representation of the force diagram. This is how we can show our force diagram, where this box is representing the object. But in Newton's laws, mostly we deal with free body diagrams. So free body diagrams are just the same as force diagrams. But now the object now is represented by a dot instead of a box. So now we represent the object by a dot instead of a box now. So that is the difference between the free body diagram and the force diagram. So for an example, I'll also show this. So it means that if we are doing the previous representation of the force diagram, this free body diagram, we have our F1 like that. So this is showing the direction, and we have our F2 like that. Also that is showing our direction, and we also have our F3 like that. So we've represented that. So this is how we draw the free body diagram with our object being represented by a dot. After this session, I'm going to do a couple of examples on drawing the free body diagram, so that I can help you master how to draw the free body diagrams. So now let's just talk about the laws of motion, and then I'll end this section and I'll start showing you how to draw the free body diagrams, and eventually we are going to see how we can use all this knowledge that we acquired to do the calculations. So the calculations are something that is so nice when we're dealing with Newton's laws. So let's see the first law. So I'll not talk about the third law because I explained it in the previous section. So an object continues in a state of rest or uniform velocity unless it is acted on by an unbalanced force. So it means that in this situation, we are saying that this object that we are having is not having any unbalanced force. So it means that all the forces are balanced. So what does it mean when they say all the forces are balanced? They are trying to say it means that the up and down forces, when we add them, we get 0. So F resultant at Y is equals to 0. If we add this and this, we get 0. And also F at X, no matter how many forces you are having, it also means that F at X, if you add them, you're going to get 0. So this is when the object is at rest. So this object is not moving. So if the object is not moving, obviously it means that all the forces that are acting on the object, they are resulting to 0. Or if the object is moving at a uniform velocity, we can call this constant velocity. Constant velocity. So also on constant velocity, it means that our F net is equal to 0. All the forces are balanced, right? So this is, if you add all the forces, you get the sum of 0 newtons, because all the forces are balanced. So they are balanced forces. So one of the application of this law, Newton's first law, is when we talk about inertia. I'm sure you have heard what is inertia. So inertia is the tendency of the body to keep its motion. To keep its motion. Like we said, an object at rest will remain at rest unless an unbalanced force acts on it. So if nothing happens to this object, if it is at rest, it will remain at rest up until forever. And if an object is moving at a constant velocity or uniform velocity, so uniform velocity means that our acceleration is equal to 0, because Vf minus V initial is our acceleration over changing time. So if this is not changing, so it means that our numerator becomes 0. So anything into 0 gives us 0. That's why our acceleration is 0 in this case. Our acceleration becomes 0. So now, we explained that. So inertia, we said this is the tendency of a body to keep its motion. So that's why it is always advised that when you are traveling in a car, or howsoever when you are traveling, always wear seat belts. Always be safe by wearing seat belts. Why do they say this? Because it is said that when you are traveling in a car, the speed of the car is the speed that you are also having. So if at any instant the car happens to hit emergency brakes, so if it hits emergency brakes, just because your body is having the tendency to keep the motion, you happen to lean forward or you happen to go forward. So that's why maybe when the car is speeding, you can end up having major injuries because of your body is keeping its motion. So this is the tendency of your body to keep its motion. So this is what happens, inertia. So whenever we use Newton's first law, remember that our F net is equal to 0. So how do you notice that? You can be told that your object is at rest or your object is moving at constant velocity or uniform velocity, or your object is stationary. So when you're having these four things, a rest, constant velocity, uniform velocity, or constant velocity, just know that your F net is equal to 0. Your F net will always be equal to 0. That is Newton's first law. So now let's talk about Newton's second law of motion now. So Newton's second law now states that when an unbalanced force, F net, acts on an object now, since the previous situation or the first law we're talking about, the F net or the unbalanced force is 0. There's no unbalanced force. So now we're having an unbalanced force. So when an unbalanced force acts on an object, the object will accelerate now. So it means that now your object is accelerating. It means that your acceleration in this case is not equal to 0 now. It will cause your object to accelerate in the direction of the F net. So if the F net is applied in that way, it means that your object will also accelerate in that way. with the acceleration directly proportional to F net. So it means that our acceleration is directly proportional to F net and inversely proportional to mass. So it means that our acceleration is inversely proportional to mass. So it means that if we increase the F net, the acceleration also increases. If we decrease it, it means that our F net also decreases in that order. And then if we decrease the mass, since these are inversely proportional, if we decrease the mass, it means that our acceleration will increase because these are inversely proportional. That's why when you apply the equal forces on two different objects, the smaller one and the bigger one, right? You apply the same forces. So if you apply the same force here and the same force here, this object will tend to move very fast than this object. Why? Because acceleration is inversely proportional to mass. So this mass will cause, because it is a bigger mass, it will cause the acceleration to be small. But in this case, since that mass is small, it means that our acceleration will be very big. So we showed that our F net is equal to ma. That is the equation of Newton's second law of motion inwards. Always remember, F net is also equivalent to F1 plus F2 plus F3 plus F4, depending on how many forces that you are having. So you can expand that this also ma is equivalent to that. So after this session, it means that I'm going to talk about the free body diagrams and explain in details the free body diagrams. So if you haven't subscribed, if you are watching from YouTube, please subscribe. And if you haven't subscribed, if you are watching from Facebook, please follow our page. My name is Stifler. I hope to see you on the next session.